I have no idea what's going on. I'm back though. This one should work a lot better. Uh, yeah, just having some technical issues that hopefully, should be resolved right now. And they definitely should. I don't see any reason why not. Um, my hope was to create a setup where I could easily go back and forth between certain windows so that I could actually show you visually what problems I'm working on. But in lieu of that, not being able to do that, I'm simply just going to have to show you what I printed out, and we're going to have to deal with it that way. PDF of linear problems. In the description of the video, I just put a link to a worksheet that has the linear problems, the linear regression problems that I will be working on today. Oh, Joe, I just read all your comments right there. I'm actually flipping back and forth between screens, but that's pretty crazy. I'm also going to share this information to Twitter. Tweet. There we go. Information's been posted. Oh, goodness. Having a bit of a, well, various issues this morning. The teachers this week are allowed, and I've already done mine this morning, which is why my morning is all crazy. But the teachers this morning were allowed to go back into their classrooms, in which I went back for a couple hours, and I had to take my room apart. We had to basically break down our rooms as if we are breaking down for the summer, which is like, okay, that's fine. That's totally fine. We can break down for the summer if need be. But yeah, I don't know. It's kind of a bittersweet thing. It was like, oh, cool, I get to go back to my classroom. It's like, oh, I get to take everything apart and throw a bunch of stuff out, and I have to get out of here, and I can't interact with anyone, really. So, that was not the most pleasant of experiences. But I got to see my classroom, and I got to throw out a bunch of papers. And I got to take all my stuff down off the walls so that they can finish cleaning everything. And we'll see what happens. It's crazy times, really. But it is what it is. Anyway, I would like to get started with what I wanted to do for AP Statistics. Basically, one of the main topics that people requested in terms of reviewing was linear regression. And linear regression was, I don't even know what month we covered it, really. I want to say we covered it like December, but I really can't remember. It's been quite a while, because then after linear regression, I think we jumped to probability, which probability is another big topic, but this one is linear regression. So in the description of this video, you will find a link to a PDF, and that PDF will contain the problems that I am going to be reviewing with you. When all is said and done, timestamps will be in the description, and we'll kind of go from there. And this review will be available to whoever wants to use it. So Let's start very simply with this. Let's see how well you can see that, and then I'm going to have to zoom in a little bit, which is not a problem. There we go. Good, 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 and good. I'm going to be writing various little notes along the side of this as I do these problems. So you'll be able to see what I add as I'm going through this. And I'll write it in red so you can see it very, very clearly. Let's move that up a little bit. There we go. Good, 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 and good. Number one, all but one of the statements below contain a mistake. Which one could be true? Now, all of these problems are talking about correlation. Correlation measures the strength of the linear relationship or the linear association. If you're talking about correlation, correlation is automatically talking about linear. But it might be super strong, it might be moderately strong, it might be weak, it might have no correlation. Let's just go through them one at a time. Answer A. There's a high correlation between cigarette smoking and gender. Immediately, I'm going to cross that one out. The reason why, whenever you do correlation, whenever you do a linear regression, it has to be between quantitative pieces of data. This is categorical, thus disqualifying itself. B, the correlation between age and weight, both quantitative pieces of data, of a newborn baby is 0.83 ounces per day. That one is also automatically eliminated. The reason being, correlation, or the value of R, should have no units. Well, you can't see that part. Let me scoot that over just a tad. There we go. Good. So now you can see it. C, the correlation between a person's age and vision. Well, vision could be given a quantitative measure, perfectly acceptable, it could do it, is R equal to negative 1.04. Well, correlation, the value of R, is measured between negative 1 to positive 1. It cannot be outside that range. As a result, anything outside, automatically disqualified. D, the correlation between a species of tree, and I'm going to stop right there. I don't have to read the rest of it. Species of tree is a categorical piece of information. Even though height is quantitative, they both have to be quantitative pieces of data. So the answer is clearly E, but let's just read E just for the sake of argument. The correlation between blood alcohol level and reaction time. Blood alcohol level can be measured, I don't know, something about parts per million or some junk like that. I'm not really sure. But reaction time would most likely be measured in seconds or something along those lines. Both quantitative pieces of data. Joe, I'm not sure I want to hear your joke. You know, your sister apologized for you the last time. But anyway, back to number 2. Which statement about correlation is true? Sorry. They give you 3 choices, then obviously you have to pick which one is the correct one. But let's just see. Regression, based on data that are summary statistics, tend to result in a higher correlation. Now, if you're talking summary statistics, you could be talking something like the 5-number summary, which is like minimum, maximum, the Q1, the Q3, and the median. And those pieces of data would just give you a general idea. It's the piece of data that they use for box and whisker plots, let's just say. But it's summary statistics, let's say, instead of using however many pieces of data they have. Yeah, if you're using the summary statistics, which the median is a measure of trying to measure a central tendency, the minimum, the maximum, they would most likely, and it does say tends, it just tends. It's not that it's a guarantee that it will, but if you had those pieces of data, that's just an example of one right there, they would potentially have a higher correlation than maybe something like that. let's say. Joe, you type your joke into the chat, and I'll judge whether or not I'll remove the statement or not. We'll go from there. Anyway, but going back to this, I is potentially true. We'll talk about 2 and 3 in a moment. I have to turn this off. Come on, you. Turn off. There we. Nope, you did not turn off. There we go. What did the elephant say when he walked in on a guy changing? I'm gonna regret this answer, aren't I, Joe? I'm gonna finish my problem. 2. If r squared is equal to 0.95, the response variable, which is the y variable, increases as the explanatory variable, the x variable, increases. That would basically be describing a positive slope. The response variable increases as the x increases, etc. Well, if r squared is 0.95, you don't know whether or not the slope is positive or negative. You don't. If r squared is equal to 0.95, yes, you could find kind of the value of r by taking the square root, but r could be positive or negative, so you simply don't know. This is indeterminate. 3, an outlier always decreases the correlation. Well, what if you had a bunch of pieces of data right here and then randomly an outlier out there? If you were well, you can't really see those. Let me put those a little darker. There we go. If I was going to have a data points like this and then an outlier all the way out here, that outlier actually strengthens the correlation. So it does not always decrease the correlation. The answer to this problem is B. Let's see the answer to Joe's joke. How do you even breathe out of that thing? I'm going to delete your joke, Joe. Remove. Remove. There we go. Back to number 3. Let's make sure we can see that. There we go. Number 3. Which statement about residual plots is true? Now, residual plots, of course, talking about the distance, the either positive or negative distance a data point is away from the predicted line. A positive residual would most likely be above the prediction line, and a negative residual would be below the prediction line. Residuals are calculated by observed minus predicted, which is going to come into play later with some of the other problems that we are going to do. Which of the following statements about residual plots is true? A curved pattern indicates non-linear association between the variables. A curved pattern indicate, well, if you have a curved pattern in the residuals, yeah, that would just mean that a linear association is not appropriate. So I'd say that one's true. 2, a pattern of increasing spread indicates the predicted values become less reliable as the explanatory variable increases. That would be like a residual plot like this. Hopefully you can see something like that, where there's a bit more spread near the end, going to the right. Yeah, that's reasonable. The prediction becomes much less reliable as the explanatory variable increases. Like if you cut it off around here or something like that, then yeah, you could totally make some kind of a prediction. The residuals would be very, clustered, but obviously if you got rid of the spread, they would look scattered. Yeah, that one tends to be true. Absolutely. 3, randomness in the residuals indicates the model will predict accurately. That is not an accurate statement. Randomness in the residuals simply means that a linear model would be appropriate. It doesn't guarantee that the model will predict accurately. It's a common misconception that's not necessarily true, which means the answer has to be C. Number 4. I'll leave 4 there. There we go. Which of A through D is not a source of caution in regression analysis between two variables. Okay? If you are doing extrapolation, I mean, it's acceptable to do extrapolation, but you approach it with caution. So that is a source of caution. Subgroups with different characteristics. Well, that is another source of caution. If you had two subgroups with different characteristics, one might produce a positive linear relationship and the other might produce a negative linear relationship. But if you put them together into one scatter plot, it may just look like a parabola. One positive side, one negative side. But if you break them up to their subgroups, you might get better information. That is a source of caution. Lurking variable. Storks do not bring babies. Just because there's a correlation does not automatically indicate there's a causation. There could be a lurking variable. Absolutely, source of caution. An outlier, yes, even if that outlier goes with the data or against the data, it doesn't matter. It is a source of caution. You are to run the regression both with and without the outlier. The answer is E. All of them are sources of caution. Be careful. Let me flip 5 up there. There we go. Much better. Good. Number 5. Which statement about re-expressing data is not true? And I emphasize the word not because this does come into play. I'm going to come back to statement 1 in a moment. I'm going to come back to that one. Let's talk about statements 2 and 3 first. A curve, statement 2, a curve that is descending as the explanatory variable increases may be straightened by looking at the reciprocal of the response variable. Well, yeah, we do have a ladder of powers, which I am going to be getting into with one of the free response questions that we have later on. But yeah, it could be, or it may be straightened by looking at the reciprocal of the response variable. And we are going to be looking at those. Yeah, so that one, definitely true, but keep in mind the problem is looking for which one is not true. Statement 3. One goal of re-expression may be to make the variability of the response variable more uniform. Well, yeah, the variability of the response variable, if we want it to be more predictive or more predictable, I guess is the word I'm looking for, we're trying to straighten things out. We are. If you're talking about the variability of the response variable, we're talking about r squared. Remember, r squared is the percent of the variability in the response variable that's explained by the linear model on the explanatory variable. So more uniform, yeah, we're trying to make it more predictable. Absolutely, that is a true statement. So it comes down to the first statement, which if you can tell by the choices, the answer has to be A, and it is. Let's just talk about statement 1. Unimodal distributions that are skewed to the right, something like this, there we go, will be made, can you see that? Yeah, you can kind of see that. Will be made more symmetric by taking the square root of the variable. No. If you're talking about unimodal distributions like the histogram that I just did, that is not a scatter plot. That is not a scatter plot. Skew to the right is talking about histograms. But if you're talking about re-expressing data, that has to do with scatter plots. Comparing two variables to each other. Unimodal distributions like the one I just drew, that is not describing two variables, that is describing one variable. The answer is A. Number 6. Over the past decade, a farmer has been able to increase his wheat production by the same amount, or same number of bushels each year. His most useful predictive model is probably MER. Well, pretty straightforward. It's not a trick question. Answer is B. Whereas another farmer has increased his wheat production by about the same percentage each year. Same percentage each year. So that's something like 20%, 20%, 20%, 20%, or something like y equals a times 1.20 to the x power, or something like that. And of course, this is exponential. This just goes back to your previous years of mathematics. If you're dealing with percentages, you're dealing with a geometric increase. Geometric increases are exponential. So, yay! Let's talk about number 8. Let's see if we can get that on there. There we go. Good, good, and good. Now this is a re-expressed equation. Give myself a little room at the top. There we go. The model, the square root of strength hat, that is strength hat, square root, equals 12 plus 20 times diameter, can be used to predict the breaking strength of a rope in pounds from its diameter in inches. According to the model, how much force should a rope 1/2 inch in diameter be able to withstand? Now, I want to be very clear about something. Strength has the hat over it. This equation is predicting strength from a given diameter, not the other way around. You can predict the strength, you can predict the STR from a given diameter, not predicting a diameter from the strength. If you were wanting to flip the variables, a regression would have to be rerun in order to do that. So please keep that in mind. But 1/2 inch rope, that's just a matter of taking 0.5 and plugging it into the equation. That gets you 22. But 22 is not the answer. 22 is definitely not the answer. See, because this is the square root of strength hat equals that equation. The square root of strength hat equals 22, which means you would have to square both sides. You square both sides, you get an answer of E. Number 9. A scatter plot of log y versus log x. Now, this is a re-expression done to both variables. They took the log of all the x values, they took the log of all the y values. Reveals a linear pattern with a very little, with very little scatter. Some junk like that. It is probably true that, ... Now, if they had very little scatter, a linear pattern with very little scatter, let's just make a prediction that it's like, I don't know, something like that. Very little scatter. But they had to re-express everything. They re-expressed the log of x, they re-expressed it as log of y. Now, as a result, let's just go through it a piece at a time. A, the correlation between x and y is near 1. Now here's the issue. It's definitely not. They had to re-express both x and y using log. And because of that, the reason for that is because the original x and y did not produce anything that formed a linear relationship. So definitely wrong. B, the correlation between x and y is near 0. Not necessarily. If the correlation is near 0, it could be like a quadratic. It could be a square root looking thing. It could be anything, really. It is probably true that the correlation between x and y is near 0. There's no guarantee to that whatsoever. You've no idea. Get rid of that. C. The scatter plot of y and x shows a linear association. We just talked about that for part A. It didn't show any linear association, which is why they had to do the log of both the x and the y in the first place. D. The residual plot for the regression of y on x showed a curved pattern. Well, most likely, yes. if there was some form of a curved pattern, if there was some form of a curved pattern, then they had to do the re-expression in the first place. The answer is indeed D, by the way. Let's see why E is wrong. E is wrong because the calculator's ln reg function will model the association between x and y. Not necessarily. They did log, and ln is natural log. Joe, are you back? Hey, Joe. What's up? Anyway, you ask your question. I'm going to go to number 10 real quick, because number 10 is an interesting question unto itself. And it's the last multiple choice before we go to the free response. Oh, nice. Had to flex. Yeah. I got, that's pretty solid. Anyway, I don't know much about, computers and water cooling, but, sounds good. But let's talk about number 10. If the point in the upper left corner of the scatter plot is removed, what will happen to the correlation? What will happen to the slope of the line of best fit? Definitely, absolutely, the correlation will increase. It will definitely increase, which means A is wrong, C is wrong, and E is wrong. It comes down to B or D. B or D. Now, the slope is interesting. This is what the slope will become. Right here, this line right here is what the slope will become, give or take, if we remove that point in the top left corner. Oh, sorry, I'm reading what Joe's saying. But now comes the question, well, what was the original slope with that outlier? Now, unfortunately, it's a little hard to see. Oh, it's a little darker. That's not my point, though. It's a little hard to recognize the fact that what I have, this dotted line, is what the slope would have been, or what that slope tried to be with that outlier. And when you remove that outlier, it actually increases the slope. The answer is B. Both will increase. A lot of people might automatically say, oh, well, of course, this is what so the slope would decrease. But the problem that a lot of people don't recognize is the fact that the y-intercept is actually also pulling that thing up as well. And when you remove that outlier, the y-intercept drops, causing that slope to increase. It's a very weird kind of mental picture that you have to recognize. All right, let's talk about number 11. First of the free responses on these pages. There we go. Subaru costs. Data collected from internet ads for 1999 Subarus were used to create a model to estimate the asking price of the car based on the number of miles it had been driven. The model has R squared equal to 0.47, and an equation of price hat equals that equation. The plot of residuals versus the predicted price shown. Do you think you could make accurate estimates of Subaru prices with this model? Now, there's a couple things to think about. Number one, yes, the residual plot is scattered. Absolutely. Yes, the residual plot is definitely scattered. So you might think, oh, well, a linear model is then definitely appropriate here. And, you could use that as evidence to show that a linear model is appropriate. But that is not what the question is asking. Look back as to what the question is actually asking. The question is saying, do you think you can make accurate estimates of Subaru prices from this model? Go back to the definition of R squared. Go back to the definition of R squared. If you're looking at the definition of R squared, and I'm going to read it for this particular problem. My price is Y, and my miles is my X. I'm trying to get a logo idea for myself. Joe, I can't help you with your logo idea. I'm trying to teach a lesson. Anyway, for stream and stuff. Anyway, so if I'm talking r squared, that's 47%. You could say 47% of the variability in price is accounted for by the linear model on miles driven. Something like that. 47% of the variability of price is accounted for by the linear model on miles driven. Do you think you can make accurate estimates? Unfortunately, no, you can't. Or, yeah, I mean, that would be the takeaway. 47% of the variability is accounted for? That is not a lot. That is less than half. That is less than half. Shouldn't be doing that. So you could just say, do you think? No. R squared is equal to 47%. And you could say something to the effect of 47% of the variability of price is accounted for by the linear model on miles driven. That pretty much sums it up. No, Joe, give me 47% of the profit. That's okay, Joe. I'm good. Interpret the slope. Now, the slope is negative 0.11. But what does that mean in context? Now, there's two things I want to say to that. Number one, change of y over change of x, which is the change of price over the change of miles driven. But when they say interpret, they're going to want a little bit of a statement here. Now, what you could see is, well, yeah, you're losing 11 cents for every mile driven. Now, you want to use the word predicted, or approximated, or estimated, or something along those lines when you write out the sentence. But the sentence could be written as, there is a predicted 11 cents lost, or decrease in price, or whatever way you want to write that. There's a predicted 11 cents lost for each mile driven. Definitely make sure you include the word predicted or estimated or something along those lines. That would be appropriate. Finally, part C. One of the cars in the data set has been driven 42,000 miles. How much was the owner asking for it? Actually, let me bring this back down a little bit. Come on, you. There we go. I need to see this graph at the top. Perfect. Okay. So if you're talking 42,000 miles, yes, you could plug in the 42,000 miles into the prediction equation, and it spits out $10,707. But that is not your answer. That is not your answer. That is a predicted model. We used the prediction equation in order to get that value. And since, again, one of the cars in the data set, they're talking about an actual car, an observed data point. It was driven 42,000. How much was the owner asking for it? The reason why we need this number will become apparent in a moment. Let's look up to the residual graph, I should say. 10,000, 11,000, 12,000. Halfway between would be 10,500, which means this is the data point that we are talking about. One of the cars in the data set, that's the car. It's been driven 42,000 miles. How much was the owner actually asking for it? Not what can we predict he asked for it? What did he actually ask for it? The residual that he has here is plus 1,000. Which means he asked for $1,000 more than we predicted. He asked for $1,000 more than he predicted. You could also get that by knowing that a residual is equal to the observed data point minus the predicted data point. If 10,707 is the predicted and 1,000 was the residual, it's very easy to figure out 11,707 was what he actually asked for it. Let's take a look at number 12. Now, number 12 is going to involve some calculator use. It's very easy to do this on a graphing calculator, which I will show you in a moment. But let's walk through this piece by piece. Number 12. Doctors studying how the human body assimilates medication inject a patient with penicillin and then monitor the concentration of the drug in the patient's blood for several hours. The data are shown in the table. Part A is asking you to straighten the scatter plot by re-expressing these data and create an appropriate model for predicting the concentration of penicillin. Well, it's asking for us to re-express the data. Let's see what we got here. I'm going to have to enter in this information. Just double check, make sure I got them all correct. Good to go. Now, with this data, let's just take a look as to what it looks like. It's already set to scatter plot. Zoom 9. There's the data. Clearly, it's curved. You could run a linear regression if you wanted to. linreg L1, L2, which obviously, or I'll just type in L1, L2. Oh, you know what I didn't do? And most of you will remember, I did not turn my diagnostics on. Let's turn my diagnostics on. Boom. Let's rerun that. Boom. Look at that. Wow, look at that R squared. Look at that R. That is strong. But clearly it's curved. They want us to re-express this data even though the R was very strong. In fact, if you looked at the residual, there we go. Clearly there's a curve in the residuals. The linear model is not appropriate. So we are going to have to go about re-expressing our data. Now, just to give you a little reminder, and I'll write this off to the side over here, there is a table, I should say, something along the lines, or a ladder, that's what they called it, a ladder of powers in terms of re-expressing your data. Something along those lines. Can you see that? You can't see that. I'll move it over. There we go. Much better. Now, the ladder of powers basically is asking for you to take your, well, for the most part, your Y values. You could do your X values. You could do a combination thereof, but this is the basic ladder of powers. And you re-express your Y values based on a certain power. Now, obviously, 0, you're raising everything to the 0 power is not going to do anything, but 0 was asking for you to take the log. -1 power would be the reciprocal, and -1/2 power would be 1 over the square root of y. This is the ladder of powers. And basically what I'm going to do is I am going to re-express my L2 list, my list 2, using this ladder of powers. I'm going to start at the top and work my way down. And we're going to see which one gives us the best kind of graph here. Now, this is the original. L1, L2. Here's the original. Clearly, there's a curve. Let's see if we can't straighten that data out. What I'm going to do is I'm going to go to L3, and I'm going to do L2 squared. And that gives me my data there. Let's just see. I'm going to have to change this to L3. Zoom 9 it. More curved. Definitely not helpful. So, let's change it to the square root. The square root of L2. Okay. It's already set to L3. So zoom 9. It looks better. Definitely has a slight curve to it in the middle. So, let's go back to our data. I'm working my way down the ladder of powers. Let's do log of L2. Let's zoom 9 it. That looks a lot better. Definitely a lot better. Just for the sake of argument, let me do the next one, just to see what happens. You don't always have to do this. 1 divided by L2. To go to the next one after you found one that looked really good. But you can clearly see that when I do 1 over y, it's curving back again. So, log seems like my best bet here. So let me read what the question's asking again. Straighten the scatter plot by re-expressing these data and create an appropriate model for predicting the concentration of penicillin. Clearly, it looks like log is the best bet. So I can run a linear regression using L1 and L3. L1 and L3. I'll take care of the log in a moment. I get all of these wonderful numbers here. Look at that r squared and r. But again, I'd have to make sure the residuals were actually, the residuals should be curved, actually. Let's double check the residuals. Because once I ran that linreg, it automatically calculated residuals. Let's zoom 9 it. Oh, I mean, yeah, there definitely seems to be like kind of a pattern, but in reality, it's like, that is as scattered as we're going to get it, really. With that linreg, your slope was negative 0.169 x plus 1.789. Now, it's not exactly y hat equals because we had to do a logarithm of the y values. So, it was log of y hat. Keeping in mind that this was x and this was y. But that's my equation. That's the equation that I'm looking for. Then it's asking you in part B, use your model to estimate what the concentration of penicillin will be after 8 hours. Again, this is predicting the concentration based on the number of hours, not the other way around. If they wanted you to predict the number of hours using this equation, you would not be allowed to do it. This predicts concentration. This does not predict hours. So, let's plug in that 8. Log of y hat, I'm going to move the camera up in a moment, equals negative 0.169 times 8 plus 1.789. If I were to very quickly do that calculation here, negative 0.169 times 8 plus 1.789, I would get log of y hat equals 0.437, which clearly is not my answer. But in order to get rid of logarithm, this takes you back to algebra 2 and to pre-calc. In order to do this properly, you would have to do 10 to the power of both sides. This is log base 10, and the inverse of a logarithm is going to be an exponential with base 10. So y hat would be equal to 10 to the power of 0.437, which is approximately 2.735 units per cc. That would be appropriate. Let's talk about number 13. Number 13. Suppose that both blood pressure and cholesterol levels of adult women can be described with normal models, and that the correlation between these variables is 0.6. Hold on. There we go. If a woman's blood pressure places her at the 88th percentile, they talked about it being normal. They want the 88th percentile. Let me just, I haven't even read the rest of the question yet, but I just want to calculate this real quick, just so I have it for a little bit later on. Let's do inverse norm of 0.88, which is approximately 1.175. Again, if you're talking normal, which obviously they're comparing two variables, so this isn't exactly what they're dealing with, but Talking about the 88th percentile right there. Now, at what percentile would you predict her cholesterol level to be? Interesting. Her blood pressure is at the 88th percentile. At what percentile would you predict her cholesterol level to be? Now, there is a formula that we haven't used that often, which compares z-scores within a linear model. But it only works if if both individually can be described as normal, and there's some relationship between the two. So, like if you were to do a histogram of blood pressures, they would be normally distributed. If you were to do a histogram of cholesterol levels, they would be normally distributed. But there's a correlation of 0.6 between the two. Well, a z-score of x times that correlation would give you the z-score of y. This is the z-score of the 88th percentile. 0.6 times 1.175 gives me approximately 0.705. Now, mind you, again, that's still a z-score. They want to know what percentile. So if I were to do that for wherever 0.705 is as a z-score, they want to know what percentile that represents. So I'm going to do a normal CDF, small number, comma, 0.705, and let's see what happens. Normal CDF, small number, comma, 0.705. Yep. Approximately 0.76, or the 76th percentile. That would be the answer I'm looking for. Nice. There's one more problem to do today, and it is, I'm going to zoom a little bit back out. It is one problem that takes up an entire page. There we go. A forester would like to know how big a maple tree might be at age 50 years. She gathers data from some trees that have been cut down and plots the diameters in inches of the trees against their ages and years. First, she makes a linear model. The scatter plot and the residuals are shown. Now, before we get to any of the questions, the regular linear model clearly looks like it has some sort of curve. The residual graph, exaggerates that curve a bit more, but the residual graph shows a clear pattern, which means a linear model is not appropriate. But that's not what Part A is asking. Part A, describe the association in the scatter plot. If you're describing the association, you're going to want to describe direction, strength, and form. Direction, strength, and form. The direction is clearly positive. The form, not linear. The strength? Well, again, we're not talking about the correlation. They're not asking you to describe the correlation. They just want to know the association. So I would say a positive, moderately strong, non-linear, or curve. I don't know what kind of curve that is. I don't. Could be anything. Could be quadratic. Could be square root. Could be logarithm. Who knows? Part B. Do you think the linear model is appropriate? No. Definitely not. And you could say that because, well, clearly there is a curve in the original scatter plot, but you could also say no, residual graph shows a clear pattern. Remember, in regards to a residual graph, if there's a clear pattern, all that it means is that a linear model is not appropriate, and that is exactly what this problem's asking for. Part C. If she uses the model to try and predict the diameter of a 50-year-old maple tree, would you expect that estimate to be fairly accurate, too low, or too high? Now, let's just get one thing very clear here. 50 years would definitely be extrapolation. Extrapolation is outside of the observed data points. But extrapolation can still be done, it just must be done with caution. That's not the answer to this question, I just wanted to point that out. Now, if you were to talk about some kind of curve here, like that curve that I just drew, hopefully it actually would represent the direction of that data. What would be the estimate for 50 years? Well, 50 years would be, it would definitely be below the prediction line. It would be below the prediction line. So would you expect the estimate to be fairly accurate, too low, or too high? Well, if the observed data point is way below, the prediction or the estimate is going to be way too high. It's going to be too high because 50 years would follow the curve downward. The prediction line would be far above it. Something along those lines. Now, there's two more parts, but now she starts re-expressing her data. Now she re-expresses the data using the logarithm of age to try to predict the diameter of the tree. Here are the regression analysis and the residual plot. Well, the residual plot's clearly scattered based on the re-expression. I mean, it looks pretty good. Explain why you think this is a better model. Well, no obvious pattern in residuals. Perfectly acceptable. But now using this model, predict the diameter of the maple tree at age 50 years. In terms of the printout, you're not going to need this. You need these two numbers, the two coefficient numbers. The constant is your y-intercept. The other one is going to be your slope. But now keep in mind, look what they did. Look what they did to the slope. When she re-expressed her data, she used logarithms on her x values, not her y values. This is not very common, but it's what she did in this problem. So, y hat equals 15.0701 times log of age, which y hat should really be diameter. There we go. Or diameter hat. Minus 8.60770, which is your y-intercept. Got to be able to read those printouts correctly. Now, yes, using this model, predict the diameter at 50 years. Yes, extrapolation. And you could make a comment to that effect, that this is definitely extrapolation and should be done with caution. But you can still go ahead and do this. It's perfectly acceptable. So, if I'm going to plug in that age of 50, I'll just do 15.0701 log of 50 minus 8.6077. And that gives me, if I plug a 50 in right there we go. it gives me a predicted diameter of approximately, well, you can see it right here, 16.995 rounds up, rounds up, rounds up, approximately 17. But what is it measured in? Diameters are measured in this problem in inches. It says it in the opening part of the problem. Now, there's a lot more that I can talk about in regards to linear regression. With those questions, I hopefully, when we do an overall review of the course in terms of a live video, hopefully you can have those questions ready for me then. But this is what we got. So, if you have any questions, make sure you email me. I'm going to be coming out with more review videos as the week comes out, and there will be an assessment, a brief assessment in regards to the information that I just gave you, which we'll talk about. We'll see you next time.